Hello, my name is Anna Poskrobko. I would like to talk about stability and chaotic properties of nonlinear Lassota equation in Orlich spaces. These results have come into being thanks to the cooperation with Professor Antoni Leon Dawidowicz from Jagiellonian University. I would like to start from classical Lassota equation, and it's known that first-order partial differential equations are frequently used as a mathematical model of the population of cells. In particular, such equation describes the process of the reproduction of red blood cells. It describes the growth of the cells, which constantly differentiate, change their properties in time, and this equation appeared in papers by Lassota and Warzewska. Therefore, in the literature, it's mainly called as the Lassota equation, or less often as the Lassota-Warzewska equation or von Förster-Lassota equation. We consider this equation with the initial condition, and we assume that functions c and f are given continuously differentiable functions satisfying the following conditions, where k1 and k2 are non-negative constants. The interpretation of the quantities is as follows. C is the velocity of cell differentiation. F is the function relating with the reproduction of cells, and F is given by the following formula. And P is proliferation rate, the relative increase of cells per unit time. But here we consider a bit simpler case of the equation, where we have function c, and the right-hand side of the equation is f of u. It's the equation 1. We consider this equation with the initial condition, and c and f are given functions satisfying the following conditions. And if a is finite, we also assume that the limit of the function f equals 0. From the classical theory of first-order partial differential equation, it follows that the solution of this problem has the following form too, where u and x denote the solutions of the following problems respectively, and this solution u generates the dynamical system T. And we consider some asymptotic properties of this dynamical system T. Is the chaos in the sense of Devaney. According to the original Devaney's definition, dynamical system T is chaotic if it has a property of sensitive dependence on initial conditions in the sense of Guggenheimer. T is transitive, and the set of periodic points of the dynamical system T is dense in any vector space. But we can shorten the definitions to the two conditions because it was proved that the property of sensitive dependence on initial conditions in the sense of Guggenheimer appears immediately from transitivity of the system and density of the set of periodic points. The appropriate proofs can be found in Banks and all for discrete in time system, and in the Lachowicz's paper for continuous case. So we can reduce this definition of chaos in the sense of Devaney. We also consider strong stability for dynamical system T. We consider these asymptotic properties in Orlich space. It is known that function phi generates Orlich space, and phi denotes phi functions. It means it is continuous and non-decreasing function, such that phi of 0 equals 0 and phi tends to infinity as arguments tend to infinity. And the modular space X will be called Orlich space and denoted by L to phi. It's the space of all X for which the integral of the following integral tends to 0 as beta tends to 0 on right side. And Matuszewska and Orlich consider some quantities which describe any phi function. For a phi function, we can define quantities ma, m0, and m infinity in the following forms. All the above functions are non-decreasing, some multiplicative, and are equals to 1 at the point 1. Using these quantities, we can define number p and q with suitable indices I. We call these numbers as Matuszewska-Orlich indices, lower and upper index respectively. So p is lower index and q is upper index. However, in our work, we don't use this original Matuszewska-Orlich definition. We use its modified version after Montgomery-Smith. We denote lower index by underline P and upper index by overline Q. And we consider the following inequalities for the function. Of course, we have the following inequalities for the lower and upper index. And in the sequel, we will assume that phi function satisfies the delta 2 condition. It means that for some omega, positive omega, we have the following inequality for all non-negative u. It forces the separability of L-phi space and the continuity of modular rho and the conditions that upper index is finite. The example of Orlich space is Lebesgue space LP. It's the Orlich space with the following modular. For p greater or equal 1, the modular is convex and the space LP is a Banach space. And for p from the interval 0, 1, the modular is convex and such Orlich space is only the Fréchet space with the following F norm. In a few papers, we describe the asymptotic behavior, but the linear version of the Lassota equation. So we have function x, and the right-hand side is equal gamma multiplied by u, and is the equation 3. And we consider this equation with the initial conditions, the following, number 4. And this equation has the unique solution, and this solution generates the dynamical system T with tilde. Problems of asymptotic behavior of this dynamical system T with tilde is well described in standard functional spaces, especially in the space of LP, Lebesgue space. And for linear equation in LP space, we have one critical value for the coefficient gamma is -1 over p, and if gamma, which is the coefficient from this right-hand side of the equation, if gamma is greater than this critical value, the dynamical system T with tilde is chaotic in the sense of Devaney. In the case of the opposite inequality, we have the strong stability for this dynamical system. If we try to generalize these results and consider Orlich space L-phi, then we get two critical values, -1 over upper index and -1 over lower index. If gamma is greater than this one critical value, we have chaos in the sense of Devaney, and if gamma is less or equal this second critical value, we have strong stability. And we can illustrate this situation on the following diagrams. In the case of Lebesgue space, lower index and upper index are equals p, and we have the following situation for the coefficient gamma. We have, for the values of this coefficient, we have chaos on the right-hand side and stability on the left-hand side of this critical value. In the case of Orlic space, we have two critical values, chaos on the right-hand side and stability on the left of this second critical value. The question is, what is asymptotic properties in the case when coefficient gamma, the value of the coefficient gamma is from the interval between these two critical values. We have some easy example that give only partly answer. We consider the following Lasota equation where gamma is negative, and we consider this equation with initial conditions where v is function in the following form, and we can show that modular of t is greater than 1, so the solution of the equation doesn't converge to zero. It contradicts the stability of the system. So for gamma from this interval, we have lack of stability. Unfortunately, we can't resolve the problem of the lack of the chaos on the same interval. We can't construct the appropriate example, so the question stays still open. The similar situation we have if we consider the Orlic space with some norm μ equals x to n, then we have also two critical values, but with some translation. We back to nonlinear equation 1. I remind that we have a nonlinear equation with initial conditions, and a solution of this equation generates the dynamical system T. We can try to find any connection between a linear and nonlinear equation, Lasota equation, and we can construct the following operator A defined on L-phi space or Lie space by the following formula, and we assume that gamma equals lambda 2 over lambda 1 when lambda 1 and lambda 2 are the following limits. Then if the operator acts on Orlic space L-phi, we get the Orlic space generates by another phi function psi, and it's the Orlic space with any measure μ, and phi functions psi equals phi of x to lambda 1. And thanks the construction of such operator, we can we get the connection between a linear and nonlinear equation. And if u and u with tilde are the solutions of the equation 1 nonlinear case and 3 linear case respectively, we have the following equality using this operator A, and hence the following diagram is commutative. So thanks this connection, we can, thanks the construction of this operator, we can transfer asymptotic properties of the linear version of the equation to the nonlinear version of the Lasota equation. And we have formulated the following conclusion. If we have lambda 1 and lambda 2 defined by the following limits, and we consider the following quantity, lambda 2 over lambda 1. Then for the dynamical system T, we have two critical values, and we have chaos in the sense of Devaney on the right hand side of the first critical value, and stability on the left of the second critical value. And we can also transfer the remark about lack of stability, and still the lack of the proof of lack of chaos for the dynamical system generated by nonlinear equation is still open. Thank you for your attention.